Hello everyone, this is Chenggong. Today I'm going to test the three most popular Python packages for MD trajectory analysis. They are mdtraj, MDAnalysis, and pytraj. If you have never heard of them, you can Google or watch my video. In today's example, I'm going to demonstrate a simple conformational analysis. We will focus on track channel, which is the potassium channel. The M4 helix of track channel has two conformations, up and down. Experimental and computational evidence suggests the up conformation is conductive while the down conformation is non-conductive. Now my simulation has finished and I would like to check whether in my simulation the M4 helix stays up or down. In this structure, you can see that the 16159 and the 284 are very close in the up conformation. We can use this distance as a collective variable to measure up and down. Actually, I'm running the simulation on the double cis mutation from this paper. If you look at the crystal structure of the wild type, they are not cysteine. This glycine and proline are also very close. We can also measure those distances. Now I come back to the terminal, and let's write those code in practice. First, I'll do mdtraj. I already have those two files. So with mdtraj, you can do a iterload. md.iterload. With iterload, you can provide a trajectory file and a top file. Here I use the PDB as the top file. And I also say chunk equals 100, which means I asked mdtraj to load 100 frames every time, so that the traj will contain 100 frames in each iteration. So here I'm going to select the atom. As I already mentioned, we want to measure the distance between cysteine 159 and 284. Atom 1 is equals traj top, name C alpha res ID. So actually in mdtraj it should be res sequence 159. And to be sure, I also give it the name cis atom C alpha index 159 and name cysteine. And atom 2 trajectory cysteine 284. So here I'm using the GitHub Copilot, so it automatically prompts some code. And I also want to measure the proline 155 and the glycine 280. So proline 155. As this protein has two chains, actually I want to measure the 159 on chain A to the 284 on chain B. So the 81 would select two atoms, one on chain A, one the other on chain B. I would like to measure the atom 1, 0 to atom 2, 1, and the atom 2, 0 to atom 1, 1. the same as atoms 3 and 4. Let's first break here, and the test is called That's why we need testing. Okay, now the distance has the proper shape. Because we have 100 frame each time we did the interlope with 100 chunk 100, and then we measured 4 distances, so the second dimension would be 4. Now let's make a list to save the distance. And use pandas to save the results to a CSV file. So we have system 159, A to 284, B to A to B. And DF to CSV. Okay, that's it. Data frame. Okay, let's open the result in VS Code. Okay, now we have the distance. Let's do the same thing with MDAnalysis. Okay. In MDAnalysis, the trajectory is wrapped in an object called the universe. At the first, this universe seems to be a little bit awkward, but later you will realize this universe actually packs a lot of feature that is really necessary for interload. With the universe, we can do the atom selection. Actually, now is res ID. See our res name system. And we can also select the chain. The system 159 on chain B. And atom 3 would be system 284 on chain A. Atom 4, the system 284 on chain B. And also the proline glycine, the proline, and the proline glycine and the glycine. Without atom pair, we can start the trajectory iteration. TS in trajectory. Actually, this part, I'm not going to use the prompt from Copilot. I'm going to do this myself. Distance 1, atom 1 with the default backend. This is 2. Actually, I need atom 1 to 4 because we want the cysteine 159 on chain A to 284 on chain B. So 1 to 4 and 2 to 3. Distance 3 from 5 to 8. And 6 to 7. And let's also write prepare a list to save the result. Actually, calc bounds would return a numpy array, but we only need the value. So I pick up the value and put that into the list. After the iteration, we can save that into actually we don't need that, so we can create the data frame. Column cysteine 159, cysteine 159. To CSV. Okay. Let's also break here to make a test. Chain unexpected selection string chain. Oops, I should end the chain ID. Because MDAnalysis use angstrom as the unit and the mdtraj use nanometers, so this number is 10 times larger than the mdtraj. I think we just got the correct number. So let's remove this break and run the distance. Let's open the table and see. Nice. Now let's do the same thing with pytraj. Actually, pytraj also provides the same iter load. But the difference in pytraj is that pytraj inherits the residue and atom definition from amber, so there's no definition of chain, and the residue always starts from 1. So that causes the problem. If we open the PDB file, we can see our residue index actually start from 27, So the residue that I mentioned earlier with the cysteine 159 actually comes from 27, but in pytraj it can only count from 1. So 27 in the PDB would be 1 in pytraj, and chain A has 27 to 287. So 287 corresponds to 261 in pytraj. So our 159 corresponds to 133, 284 corresponds to 258. And the chain B started from 27 in our PDB file, but in Amber it's 262. Actually, the distance is pretty easy. The only thing complicated is the selection. So now the cysteine 159 on chain A is residue 133 on. So 133. Let me see, alpha to 258. 132. Residue 51. Let me see. So now you see the GitHub Copilot doesn't really understand what we want to measure. So now the cysteine 284 on chain A2 would be 258 to 394. So that would be 258 to 394. Let's see. And also with the glycine and the proline. Oh, I forgot the end. One 133.51, 258.394, 129.5, 15.392, 54 atoms. So actually, this object traj from iterload would iteratively load the trajectory only when necessary. So this trajectory with this distance function would do the iter load, like load one frame at a time, analyze next frame, next frame. So now the distance contains the data we need. So now we create the data frame from pandas. To CSV. I think it should be transposed. There's another problem with pytraj. From the Amber, they only provided the pytraj with Python 3.7. They didn't provide the pytraj with later, like 3.11 or any newer Python version. So I need to switch to another counter environment. That's pretty quick. Okay, we get the same result. And I also do the same distance testing in GMX distance and the CPP with the GMX lib. And I also have this bash script to test each one of them and see who is the fastest. Up until now, I presented 5 ways to measure distance. The running time is listed here. The C++ is absolutely the fastest. However, it is also the most difficult to maintain. Pytraj and MDAnalysis are slightly slower, and I would say they are internally well optimized. Besides speed, we also care about the user-friendly. As you have already seen, MDAnalysis has a very intuitive, object-oriented interface. Its selection syntax closely mirrors how we conceptualize a protein. We can select by chain, residue, and atom using indices and names. Once a selection is created, it is actually a reference that points to the current frame. When you loop over the trajectory, this reference automatically updates to the current frame. This makes it very easy to do interload. Pytraj also has impressive performance, which doesn't come as a surprise, given its origins in Amber's CPP traj. However, it also inherits some of Amber's shortcomings, such as residue ID always starting from 1, and the lack of chain definition. And for mdtraj, I would say it is outdated. It's slow and not flexible. After all the testing, I find myself leaning towards MDAnalysis. Only if I'm in desperate need of speed, I would consider writing some C++. So what do you think about trajectory analysis? Please leave your comment below. This is Cheng Gong. See you in the next video.